Lecture 11 is Reactions of Alkenes, Part 1. We're dividing Chapter 8 in Wade into two parts, simply because there are so many reactions of alkenes. Remember that in our last lecture, we looked at structure and synthesis of alkenes. Specifically, that was ways to make alkenes. And for the next two lectures, today and next time, we're going to be looking at reactions that we can do on alkenes to transform alkenes into other functional groups. Remember, when we started alkenes last time, I mentioned that they're a very synthetically useful functional group because you can transform them into lots of other things. Before, we looked at this reaction map where we kind of combined many of the reactions that we learned into one picture, where we kind of tied everything together. We started with a cyclohexane. We did a free radical halogenation using either NBS, remember that was N-bromosuccinimide, and light. The other reagent, of course, is Br2 and light. So we can add a halogen to an alkane. From that, we can eliminate it with a strong base and heat to make a double bond. We could also substitute it with a good nucleophile at room temperature to get the substitution product. In this case, we're using hydroxide to substitute the bromide with an OH group to make an alcohol. We can dehydrate alcohols by eliminating them to get to the same elimination product as we did from the haloalkane. Last time, we looked at E2 elimination of vicinal dibromides with Ki. So we added that as another reaction here that we could use to arrive at our cyclohexene. We learned about hydrogenation, where we could take an alkene and hydrogenate it into the alkane. We also looked at using alcohols as nucleophiles to substitute a haloalkane to make an ether. Today, we're going to learn 7 new reactions that involve transforming an alkene into other functional groups. We are going to look at 2 reactions that can add a halogen to the alkene, and we can do that at 2 different sites on the alkene. We're going to look at 2 different ways that we can add an alcohol into a certain position on the alkene. Another way that we can add an alcohol to a different position on the alkene. We're going to look at a way to create an ether from the alkene instead of starting from the alcohol like we did on the previous slide. We're going to make an ether from an alkene, and we're going to add Br2 across the double bond. Notice that when we add Br2 across the double bond, we get the same starting material. We get vicinal dibromides was the same starting material that we had for the vicinal elimination. So more reactions that we can incorporate into our global reaction map. 7 today. We're going to learn 10 next time. So the general reaction that we're using today is called electrophilic addition. This can kind of fall into the category along with, we looked at E1, E2, SN1, SN2, free radical halogenation, hydrogenation. Now we have electrophilic addition, and we're going to look at 7 specific examples today involving electrophilic addition. So this reaction involves the alkene acting as a nucleophile. The alkene is electron rich. Specifically, the labile pi bond gives us additional electron density between 2 carbons, and that high density region on the molecule can act as a nucleophile and attack an electrophile. So remember, we looked at this kind of an electron potential map. Here's our sp2 hybridized carbons, our planar alkene, where we have pi density above the plane of the molecule and below the plane of the molecule. This is going to act as our nucleophile in our reaction. If we have some electrophile, some highly electron deficient species, the nucleophile will attack the electrophile by donating its pi electrons to it. We're going to see several varieties of this reaction, and they will follow this general form. The first step in the mechanism is going to involve the pi bond, again, the pi electrons, attacking the electrophile, some highly positively charged. It doesn't have to be fully positively charged. We'll see it could be partially positively charged as well, but some highly electron deficient species, and create a bond using those pi electrons to one of the two carbons involved in the double bond. Now, the carbon that gets the electrophile maintains 4 bonds. Notice that the carbon on the left here has 4 bonds, 1, 2, and then 2 in the double bond. If you break the double bond and use those pi electrons to make a new sigma bond to this electrophile, that carbon on the left maintains 4 bonds, but the carbon on the right loses the pi bond, but doesn't gain the bond to the electrophile. So it loses a bond in this reaction, and as a result, we will have a positive charge. Now we will see that we will always end up with the positive charge on the more substituted carbon. So whichever of these two carbons is more substituted, meaning tertiary over secondary over primary over methyl, whichever one is more substituted is the one that will get the positive charge. The less substituted one will get the electrophile. We'll talk about why that is in a moment. In the second step, there will be some nucleophile in our reaction, some nucleophile in our solution that will add in to that positively charged carbon and make a bond to it, giving that carbon a 4th bond. So the big picture is that the two carbons that were participating in the double bond lose the double bond. The less substituted one gets the electrophile, the more substituted one gets the nucleophile. Notice that step 2, where a negatively charged nucleophile attacks a positively charged carbon, giving it a 4th bond, that looks like the second step of an SN1 reaction. We've seen this mechanistic step before. So step 2 should be nothing new, the idea of a nucleophile creating a bond to a positively charged carbon. Step 1 is new to us though, where we're using the pi bond to add an electrophile to one of the two carbons. So let's look at our first example, our first reaction. This reaction is electrophilic addition of HBr, hydrogen bromide, or really it could be any hydrohalogen, HX. The first step of the reaction involves protonation of the double bond to form the carbocation. So in this reaction, our pi bond is going to act as a nucleophile, and it's going to attack the HBr as our electrophile. Now looking at HBr, remember that this is a very polar bond. H is going to be delta plus, Br is going to be delta minus. So H is really our electrophile here. It is electron deficient. So the pi electrons will attack that H. It'll make a bond to that H. Now remember that H can only make one bond. So it's got to lose its bond to bromide. In this sense, bromide is kind of acting as a leaving group. So we're going to put the H onto one of these carbons. The other carbon's going to get a positive charge. Now, just for a moment, notice that these carbons are identical. This molecule is symmetrical. So at this example, it doesn't matter what carbon the hydrogen goes on. It can go into either of the carbons that were involved in the double bond. So we've got a positive charge now, and we've got bromide floating around in our solution. In the second step, bromide is going to act as a nucleophile. Remember that in SN1, we don't need a strong nucleophile because that nucleophile will be highly attracted to the largely positive carbon. So we can have a weak nucleophile add to our C+. That gives us our product. Again, we have added the H to one of the carbons involved in the double bond and the Br to the other carbon involved in the double bond. We've basically split our electrophile in two, added one part of it to one and one part of it to the other. Now, like I said in the previous example, the carbons were identical. You can go back and look, our molecule was symmetrical, and so it didn't matter what H the carbon went on to or which carbon got the positive charge, because either way it would be the same intermediate. Here's an example of electrophilic addition of HBr to an asymmetrical molecule. Look at our double bond here. One carbon's got two methyl groups on it. The other carbon has a methyl and a hydrogen. So now we have two different products, potentially, depending on the way that the reaction goes. If we add the H to the carbon on the right and the bromide to the carbon on the left, we get this product. If we add the H to the carbon on the left and the bromide to the carbon on the right, again, the two carbons involving the pi bond, we get the product on the right. Now, like I've told you, we only get one product. We have a way of predicting which product we get. It turns out we get the product on the left and not the product on the right. Two different products, but only one of them forms. Why is that? I hinted at it before. Notice the first step in our mechanism. If when our double bond adds the H, it adds the H to the right carbon on the right, then we get a tertiary carbocation. If we add the H to the carbon on the left, we get a secondary carbocation. If you don't remember tertiary and secondary, go back and look at chapter 4 when we looked at free radical chain reactions and talked about hyperconjugation. A tertiary carbocation is more stable than a secondary carbocation because you have more electron-rich groups overlapping that electron-poor carbon. So the mechanism will proceed in whatever direction will give the most stable intermediate. We will never add the hydrogen to the left, carbon in this case, because that gives us a less stable intermediate. This is called Markovnikov's rule. Remember when we looked at E2 and E1, we learned about Zaitsev's rule, which gave us a way to predict the major product in an elimination reaction. Here, we're learning the way to predict the major product in an electrophilic addition reaction to alkenes. Markovnikov's rule says that in an electrophilic addition to an alkene, the electrophile adds in such a way as to generate the most stable intermediate. We call this the Markovnikov position, the position that gets the halogen, basically the most substituted position involving the double bond. This one right here, this is di-substituted, this is mono-substituted. Whichever side is most substituted gets the halogen. We call that the Markovnikov position. The same way that Alexander Zaitsev did hundreds of elimination reactions to generalize his rule, to figure out the trend, Markovnikov did the same thing. He did a bunch of different reactions involving addition to alkenes, and he showed the orientation of HBr to alkenes in 1869. Another way to write Markovnikov's rule says that in an electrophilic addition to an alkene, the H adds to the carbon bearing the most H's. The H adds to the carbon bearing the most hydrogens. Notice that in the alkene, our carbon on the left has no hydrogens. It's only got two methyls. It's the more substituted one. The carbon on the right has only one methyl and one H. So when we're going to decide what carbon our hydrogen goes on, the hydrogen is going to go onto the carbon bearing the most hydrogens. That's kind of along the lines with Zaitsev's rule. Remember, in Zaitsev's rule, I said the trick to remember was that there was safety in numbers, that the base removes the hydrogen from the carbon bearing the fewest hydrogens. The hydrogens on the carbon with the most hydrogens are safe. So in this case, you can think of it as the hydrogen goes onto the carbon with all of its friends. Carbon with two methyls has no hydrogens. Carbon on the right with one methyl has one hydrogen. So the hydrogen goes onto the carbon with the other hydrogens. That is Markovnikov's rule. Addition of HBr to an alkene follows Markovnikov's rule. I'm saying that because we will look at some reactions that violate Markovnikov's rule. This one obeys Markovnikov's rule. Here's another example. If we have methyl cyclohexene, one methyl cyclohexene, and we add HBr to it, the mechanism is going to proceed as follows. The pi bond is going to use its electrons to grab a hydrogen. Remember, we've got our nucleophile, our electron-rich species is the pi bond. Our electron-poor species is the hydrogen. So the pi bond will make a bond to the hydrogen. That will force bromide to let go. And now we've got a choice. Do we put the hydrogen onto the carbon with the methyl and no hydrogens? Or do we put the hydrogen onto the carbon with the hydrogen? Well, Markovnikov's rule says that we put the hydrogen onto the carbon with the most hydrogens. That will generate the more substituted intermediate. Notice that this is a tertiary carbocation. Our other option, if we were to violate Markovnikov's rule, would give us a secondary carbocation. That is less favorable. That's why the reaction does not proceed in that direction. So we'll add the H to the carbon bearing the most H's, giving us the most substituted cation. Then the bromide will attack that carbocation in an SN1 fashion, and we get our product. This would be 1-bromo, 1-methyl cyclohexene. Notice that sometimes you can get the same product starting from different reagents. Here are two different alkenes. This is 2-methyl-2-butene. This is 2-methyl-1-butene. In both cases, the H and the bromine follow Markovnikov's rule. This is a little bit weird though. Notice that the bromide has the same Markovnikov position. On our first example, our second carbon is the Markovnikov position. And in the second example, the second carbon is the Markovnikov position. So the bromine is going to go onto the Markovnikov position in both cases. The H is going on to different positions. If you want to prove that, try to write out the mechanism for each of these reactions, and you'll see where the H is going and why the bromide ends up where it does. In both of these cases, again, because the reaction is adding HBr, they're going to follow Markovnikov's rule. So we have a way to add the bromide to the more substituted position. But wouldn't it be nice if we had some way to add the bromide to the less substituted position? Notice that in this case, we're adding, whatever reagents do this, we would be adding the bromide to the wrong carbon. This is against Markovnikov's rule. This is putting the bromide on the less substituted position of this double bond. And this is putting the bromide on the less substituted position of this double bond. Wouldn't it be nice to do that? What if we had control over that? Well, it turns out that we do have control over that. There are slightly different reagents, and we call this anti-Markovnikov addition to an alkene. Now, how does this work? This is organic chemistry, so we're not going to be able to get away with just saying that H2O2 does something magical that makes this happen. We need an explanation. Let's look at the mechanism. Let's explain what H2O2 is doing that causes this to violate Markovnikov's rule. So this is quite different. This reaction, the anti-Markovnikov addition of HBr using H2O2, involves formation of radicals. And like our free radical chain reaction, follows a predictable series of steps. The first one being initiation. So in the first step, our H2O2, hydrogen peroxide, is split into two radicals. Now, here they're using a generic peroxide. They're just using ROOR, where R's can be carbons, they can also be hydrogens. But ROOR, this OO bond is called a peroxide bond, and they're quite unstable. They tend to split homolytically into two radicals. So the first step involves the peroxide bond cleaving into radicals. In the second step of the initiation, we have one of those peroxide radicals, RO dot, grabs an H from our HBr. And that gives us an alcohol, ROH, which is a byproduct. But most importantly, it generates bromide radical, Br dot. Then we jump into a propagation step, again, similarly to free radical chain reaction. Here, the bromine radical adds to the double bond in such a way to generate an alkyl radical on the more substituted carbon. So we're going to take one of the electrons from our alkene, one electron from our radical, and we're going to make a new bond to one of these carbons. The other radical that was in the pi bond gets put onto one of the carbons. So we are going to choose which carbon gets the radical based on whichever one is more substituted. Notice that the carbon on the left has two hydrogens. The carbon on the right has two R groups, has two carbons. So if we put the bromine on the left, we get a tertiary radical. If we put the bromine on the right, we would get a primary radical. Since tertiary radical is more stable than primary radical, we're going to go that direction. Again, that kind of sounds like Markovnikov's rule, but pay attention because it's different. It's the same logic, but we're not putting a hydrogen on, we're putting a bromine on. But we're still forming the most stable intermediate. Then in the second step, our alkyl radical adds to another equivalent of HBr. So our H is going to donate an electron to our radical. Our radical is going to donate electron to an H. They're going to make a new bond. That gives us our product. And we're going to be left with the bromine with the one unpaired radical, the one unpaired electron, and we're going to have Br dot left over. Notice that that Br dot can go back and participate in another step one with another alkene. So this is kind of a propagation step that cycles over and over and over. It's a chain reaction, a lot like our free radical chain reaction was. So it's backwards. And if you go back and look at the mechanism, the reason that we get the opposite orientation, the opposite preference here, is that in anti-Markovnikov addition, we add the bromine first. Here's our alkene, and bromine's going on in the first step, giving us the more substituted radical. Then the H goes on in the second step. In our first mechanism, in the Markovnikov addition, the H goes on first, giving us the more substituted carbocation. Then the bromide comes on. So because the order is different, the orientation across that double bond is different. They're not really violating the idea of more substituted intermediates being more stable. It's just reversing the order in which they go onto the double bond. All right, so we've got Markovnikov addition of HBr. We've got anti-Markovnikov addition of HBr with H2O2, hydrogen peroxide. Let's keep going. Here's a third reaction. This is hydration of alkenes. Remember, we looked at dehydration of alkenes before, where we took an alcohol. I'll just go back and remind you. We took an alcohol and used a mineral acid, H2SO4, and heat to make a double bond. This is literally the reverse process. We are taking a double bond, an alkene, and we're adding water to it. We're adding that OH group. Where's the water? Well, notice that we've got no hydrogens here. We've got one hydrogen here. After our reaction, we put our OH onto the tertiary carbon. Now we've got two hydrogens on our neighboring carbon. So we have added OH onto one carbon that was involved in the double bond, and we've added H to the other carbon that was involved in the double bond. So we are adding HOH across the double bond. And notice that this is Markovnikov. This is Markovnikov's position. We are adding the OH onto the more substituted carbon, and we're adding the H onto the carbon bearing the most hydrogens. The reagents to do this are acid and water. You can use various types of acid. It can range from mineral acid like H2SO4 or say hydrochloric acid, hydrobromic acid. Of course, if you add hydrobromic acid or hydrochloric acid, you risk going through Markovnikov addition of that HX. So that might be good to avoid if you don't want byproducts. But we need some kind of acid and water, some kind of acidified water. H3O plus, remember, hydronium is kind of a shorthand for any generic acid, any water that has been acidified in some way. So let's look at the mechanism for this. Remember that it follows Markovnikov's rule, but that does not necessarily mean that it's the same mechanism as reaction 1 that we saw. What I mean by that is the reaction does not proceed in this way, meaning we don't take our alkene and add a hydrogen to it from water. Because if we would do that, we would be generating hydroxide. And as we know, hydroxide is a strong base. We don't like to form highly reactive products. So this is not a good mechanistic step. This would be getting us very reactive products. So how do we get to our product if we don't follow this mechanism? Well, we need one extra step. The reason that we need acid here is because it's the acid that gives the hydrogen to the alkene. In the first step of the hydration mechanism, the alkene grabs a proton from our acid, H3O+. That protonates our double bond. We follow Markovnikov's rule and put the H onto the carbon bearing the most hydrogens. That gives us the more substituted carbocation. Now, we have two waters floating around. We had one water when we started with, and we have one more water that we made when we deprotonated our acid. So one of those two water molecules will add into our carbocation. Again, this is like an SN1 reaction where we are taking a weak nucleophile and adding it to a carbocation. Then we'll have water, H2O plus, on our substituent. We will then regenerate our acid by having water grab that extra hydrogen from that, put the electrons back onto the oxygen to give us neutral oxygen. We've now made our alcohol, and again, we've regenerated our acid. Our water grabbed an H+, so it became H3O+ again. So this is acid catalyzed. We start with an H3O+, we use it in the course of the reaction, and in the last step, we regenerate our H3O+. So this is acid catalyzed addition of water, H2O, again, H onto one carbon, OH onto the other carbon, across a double bond. And it follows Markovnikov's rule. There's another way to get Markovnikov addition of water across a double bond that does not involve acidified water, H3O+. It's a separate reaction called oxymercuration demercuration, and it looks pretty complicated. It's got some weird mercury reagents, and like we're going to see, it gives you the exact same product as we just saw. I'll talk about why we would be interested in using a reaction like this rather than a simpler reaction, even though it gives us the same product. I'll talk about that in a moment. But let's look at the mechanism. First of all, the overall reaction. Here's our alkene, and we've got some groups on it, whatever they are. They're not labeled in this case. We're going to use mercury acetate, HgOAC2. This OAC is shorthand for an acetate group. So we've got mercury diacetate and water. In the first step, we add OH and mercury acetate, not diacetate, but mercury acetate across the double bond, such that the OH goes in the Markovnikov position and the mercury goes in the anti-Markovnikov position. Then in a second step, a second reaction step, so we would first do this, and then we would add NaBH4, sodium borohydride, and that will replace the mercury acetate group with a hydrogen. That's the big picture, 2 steps. First, we add our OH and HGOAC across the double bond. Then we displace the HGOAC with an H, and we end up with an OH in the Markovnikov position. Here's the mechanism. In the first step, mercury loses one of its acetate groups. This doesn't actually show that in the first step, but HGOAC2 loses one of its acetate groups, and it becomes mercury acetate with a positive charge on the mercury. That is our electrophile, the Hg+. So, as is expected for these types of reactions, our pi bond will add to the electrophile. Now, there's a second kind of concomitant step along with that. Because mercury is such a huge atom, and it's got such an enormous electron shell filled with all kinds of electrons, it's got d orbitals and things all over the place. What happens is that giant mercury atom adds electron density back into the alkene that just gave up some of its pi density. So we have electrons leaving the pi bond and electrons coming back into the other carbon. What you end up forming is this 3-membered ring. You can kind of see how the left carbon grabbed the mercury and the mercury grabbed the right carbon. So now we have this 3-membered ring involving Hg+ and an acetate, and that's called mercurinium. Now, as you probably know, 3-membered rings are strained. We talked about that. As you deviate from 5 and 6-membered rings, you start getting bond angles that deviate from the ideal 109.5 degrees. So this 3-membered ring is fairly strained. As a result of that, water, which we have floating around, remember we're using water here, will add to one of these carbons and do an SN2 type reaction to displace this mercury. Look at this mechanism. Here water comes in from the back side of the carbon, the mercury acts as a leaving group here, and the electrons leave from the front side onto the mercury. So this is an SN2 type displacement that opens that 3-membered ring. It relieves that ring strain. It also gives mercury its electrons back so it can be neutral again. In the last step, water, another molecule of water, will grab an H off of that water to give us back our neutral oxygen. That's our intermediate here. Our first intermediate product is OH on one carbon and our mercury on the other carbon. That's called our organomercurial alcohol. Now, here's a question. Why does water add to one carbon and not the other? Notice that specifically we said that water will add to whatever carbon gives us the Markovnikov product. So there must be some reason why water is adding to one of these carbons and not the other. And there is a very good reason for that. Since the mercury group is very large, again, we've got this enormous mercury atom with this acetate group on it. Water is going to add to whichever carbon gives the most room to the mercury. Now, that is by default Markovnikov's rule. By water attacking the more substituted carbon, it will leave mercury on the less substituted carbon, meaning the carbon that has the fewest carbon groups on it, or in other words, the carbon with the most hydrogens. So you end up with this big bulky mercury group on the carbon that has the most room for it. There's another more chemical explanation, and that is that in this 3-membered ring, the ring is strained and mercury wants its electrons back. Can you see mercury's positive? So mercury will be pulling on both of these carbon bonds, and it will be pulling harder on the carbon that can most easily deal with that positive charge. So since the carbon on the left, let's say, is more substituted, it can deal with a positive charge the most. It does not need these electrons as much as the other carbon. So mercury will pull harder on it than the other carbon. So that will mean that we'll have more positive character on the left carbon than the right carbon. And so that's the carbon that water will attack. Either way, if you can't remember that, just remember that water adds to the Markovnikov side, the mercury ends up on the anti-Markovnikov side, and that gets us our organomercurial alcohol. In the last step, again, our second step involving NaBH4, we displace the mercuric acetate group with a hydrogen. So NaBH4 is a source of hydride, H-, which we've used H- before. If you don't remember, go back and look at the SN1, SN2, E1, E2 slides. We used sodium hydride to deprotonate an alcohol and make it into an alkoxide. Here we're using NaBH4 as a nucleophile. The H- is going to attack the carbon bearing the mercury, and it will displace the mercury in an SN2 fashion. That leaves us with an H in that position, and the alcohol still in the first position. There are other subsequent kind of steps that go along with that. The mercury acetate ends up decomposing. There's a redox reaction. Mercury gets reduced into the metal. It precipitates out. There's all kinds of other things that are going on here. But as far as the organic product goes, this is what we care about: the H displacing the mercury. So we call that oxymercuration demercuration because our first step, we put on the oxymercury group. We use it to give us our desired orientation so that we know that the mercury goes onto the less substituted side, forcing the water onto the more substituted side. And then once we've got everything in place, we then demercurate and get back to our alcohol. There's a related reaction, reaction number 5, called alkoxymercuration demercuration, which looks very, very, very similar to our reaction that we just saw. But instead of using mercury acetate and water, we use mercury acetate and an alcohol, ROH. And the result is that instead of the mercurial alcohol, we get a mercurial ether. So instead of OH over here, we have OR over here, because instead of HOH, we have HOR. So our first step is exactly the same. We'll make that mercurinium ion, but then our alcohol will displace that ring and we'll get our OR group on along with our mercury acetate. Then in our last step, the sodium borohydride, the hydride will displace that mercuric group, and we end up with our OR group left over and our H on our second carbon. Again, we still have Markovnikov orientation because it's the same mechanism that we just saw. It's just that we are making an ether now, COC-ROR, instead of an alcohol. So we have two choices. If we have an alkene and a mercury acetate, if we add water and then NaBH4, we'll get a Markovnikov alcohol. If we add an alcohol and NaBH4, we get our Markovnikov ether. Try to keep these straight. If you want to make these products, if that is the goal of your problem, is to make one of these products, you need to know the recipes and the sequence to do that. Okay, we're already up to 6. We use the last 2 reactions using acidified water to do Markovnikov addition of OH and oxymercuration demercuration to give Markovnikov addition of OH. I forgot to mention why we would want to do this. It turns out that acidified water, H3O plus and water, is a very, very, very common reaction. Very, very common reactant. It will react with all kinds of things. It will react with alkyl halides. It will react with alkenes. It will react with alkynes. It will react with carboxylic acids or aldehydes or ketones. It will react with almost every kind of functional group. It will do something unique to every functional group, but it will at least do something to every functional group. And that means that if you've got a molecule with more than one functional group on it, and you react that molecule with H3O plus and water, that H3O plus and water will add to both functional groups. You can't control it. However, the oxymercuration demercuration reaction is specific to alkenes. It will not react with alkynes. It will not react with aldehydes and ketones or carboxylic acids. So if you've got a molecule with an alkene, an alkyne, a carboxylic acid, etc., and you only want to do a reaction on the alkene, oxymercuration demercuration is the best choice. It will leave the other functional groups there alone. If your only functional group on your molecule is an alkene, then you are free to use whatever you want. Use H3O plus and water, fine. Or use oxymercuration demercuration if you want, fine. It'll get you the same product. But if you need to be specific to the alkene, use oxymercuration demercuration. So both of those reactions involve Markovnikov addition of the HOH. Now, again, wouldn't it be nice if we had an anti-Markovnikov way to add HOH across the double bond? Again, looking at 2-methyl-2-butene, an asymmetrical alkene, if we were to do Markovnikov addition of this, whatever we're adding, we're going to add that group to the carbon on the left, and we're going to add the H to the carbon on the right because it has more hydrogens. So the anti-Markovnikov reaction, whatever it would be, would reverse that. And we would add the H onto the carbon on the left, and the other group, in this case an alcohol, onto the carbon on the right. Again, anti-Markovnikov. So fortunately for us, we do have a reaction that will do that. This reaction is called hydroboration oxidation. It's another two-step reaction, like we use two-step reactions for oxymercuration demercuration. This is a two-step reaction called hydroboration oxidation. We start with our alkene and a reagent called BH3THF, boron trifluoride tetrahydrofuranol etherate. It's a weird reagent. The problem with boron is that it likes to polymerize. And so if you just use BH3 all by itself, the borons, the BH3 and the other borons will all polymerize with each other. So instead of just using pure BH3, we use BH3 that has been complexed with tetrahydrofuran. We've tetrahydrofuran before. Basically, the lone pairs on the oxygen in THF grab onto the boron and prevent the boron from polymerizing with other borons around it. So again, boron trifluoride tetrahydrofuranol etherate. But that's our reagent, and what it does is it allows us to add a BH2 onto one carbon and an H onto the other carbon. So once this reacts, the THF kind of floats away, but we add BH2 onto one and H onto the other. That looks fairly similar. We're adding H onto one and the other piece onto the other. Then in a second step, we add hydrogen peroxide and hydroxide, and that will do a replacement reaction where we displace the BH2 with an OH. Now again, there's two important details here. The first, of course, is that it's anti-Markovnikov orientation. We are adding the H onto the carbon with the most H's. That's violating Markovnikov's rule. Second is that we get syn stereochemistry. It's the first time today that we've mentioned stereochemistry. So let's look a little bit deeper into this. Let's look at why we get anti-Markovnikov orientation, what's forcing this reaction anti-Markovnikov, and let's look at what does syn mean and why do we get syn. So here's why we get anti-Markovnikov addition. Again, the same logic that we used when we looked at oxymercuration, demercuration, and we said that the three-membered mercury ring gets opened up in the direction that makes the most room for the mercury. When the H and BH2 add across this double bond, they're going to add in the position that makes the most room for the BH2. So looking at this double bond here, we've got two methyls on the left. That's the Markovnikov position. We've got one methyl on the right with a hydrogen. That's the anti-Markovnikov position. In a Markovnikov reaction, that is where our hydrogen goes. But because we want to make more room for the boron, we are going to flip that around. We're going to put the boron on the less substituted side and the hydrogen on the more substituted side. So it says boron adds to the less hindered, less substituted carbon, and hydrogen adds to the more substituted carbon. That is anti-Markovnikov. That is anti-Markovnikov. H on one side, BH2 on the other. Again, the reaction proceeds in such a way as to give the more stable intermediate. Along with that step, not only does that step give us the anti-Markovnikov orientation, it also gives us what we call syn addition. Remember that the pi bond is planar. It's got electron density above the plane of the molecule and below the plane of the molecule. When this BH3 adds, it approaches the alkene from one face, and the B and the H go on simultaneously. We're showing this transition state that's showing the carbon making a bond to the boron, while the boron is losing a bond to the hydrogen, while the hydrogen is making a bond to the carbon, and while that pi bond is breaking. All this is happening in one step, and it's happening from one face and not the other face of the alkene. It can happen in both faces, the top face or the bottom face, but both are going to go on to the same face, whichever face that is. So our intermediate, where we have the BH2 on one carbon and the H on the other carbon, those are adding to the same face. In this case, they're both adding to the bottom face. Then in the second step, when we do this H2O2 and hydroxide step, we are replacing the boron with that OH. It's a replacement reaction. Actually, it's an inorganic reaction called an insertion that we're not going to learn in this class. So we're not going to look at the mechanism. But notice that it's not SN2. It's not backside attack, meaning we're not adding the OH to the top face and displacing the boron. We're actually adding the OH to the same face. It's inserting itself in between the B and the C and then forcing the boron off. So it's a reaction that we don't need to learn about the mechanism. Just know that the OH replaces the B. Now, notice that that means that the H is on the bottom face of the ring and the OH is on the bottom face of the ring. That is always true of this reaction. We call that a syn addition. The OH and the H are added to the same side of the molecule, the same face of the molecule. Meaning that, let's say we start with a 5-membered ring like this, a planar ring. We can add BH3 in our first step, and then NaOH, H2O2 in our second step. And the result will be that we get anti-Markovnikov addition. Again, notice that the OH is on the less substituted carbon, the H is on the more substituted carbon, and they are syn in both cases. We can have them adding syn underneath the ring, and we can have them adding syn above the ring. But they are always going to be adding in the same face. The H that goes on and the OH that goes on will always be both dashed or both wedged. Both of these possibilities are possible. We don't get the diastereomers. Notice that these are enantiomers of each other. All the dashes and the wedges are inverted from one molecule to the next. So those are enantiomers. We don't get the diastereomers. We don't get any ones where the H is wedged, but the OH is dashed, for example. That would be anti-addition, not syn. This reaction is specifically syn. All right, that's 6 reactions. Let's look at our 7th reaction. Our 7th and last reaction today is addition of a halogen, addition of X2. In this case, we're using Br2 as our reaction. The first step involves electrophilic addition of the Br2 to make a bromonium ion. So what's going to happen is our alkene is going to add to a bromine, Br2, and it's going to displace a bromide. Now, the same way that our mercury fed back in to our alkene in the oxymercuration demercuration reaction, our pi bond grabbed the mercury and then it fed back in to remake that bond and give us this mercurinium ion. The same thing happens for bromonium. They're not actually showing it here, but since again bromine is so big and it's got such a big squishy electron shell, it will feed back into the carbon that loses a bond to ensure that it doesn't actually lose that bond. That gives us another 3-membered ring, a lot like the mercurinium ion, and we call it bromonium. Then we've got bromide floating around, and like the mercurinium ion, the 3-membered bromonium ion is very strained. And so the bromide will attack the back side of that ring. This is an SN2 type reaction. Bromide adds to the back side of that ring and opens up the 3-membered ring using the Br plus as a leaving group. That means that we get the bromines added to both carbons. One bromine goes on to one, the other bromide comes on and goes on to the other. We get bromines on both carbons, but they will always be anti and not syn. Notice why. Remember that since the alkene is planar, the bromonium ion can either add to the top face or the bottom face. In this case, they're telling us it's the top face. So if this case we are adding our bromonium to the top face, then when we open the ring in an SN2 fashion, that bromide has to approach from the back face, the bottom face. The original bromine, of course, will stay on the top face. So we'll have the attacking molecule on, say, one face of the molecule, and the original bromonium bromine on the top face. To illustrate, here's cyclopentene. Again, we have a planar sp2 hybridized alkene. We're going to add Br2. The product will be the trans or anti arrangement, where one bromine is up, the other bromine is down. We will never get the arrangement where one bromine is up and the other bromine is up. That would be syn addition. This reaction, adding Br2 across a double bond, always goes anti. Again, just to illustrate that, here's our planar ring. We're going to add to one face of that double bond. In this case, it's the bottom face. We're making our bromonium on the bottom face of that double bond. Our bromide has to attack from the back side, in this case, the top face. Open up that ring. So the original bromine is on the bottom face. The added bromine is on the top face. We can get the enantiomer. Of course, if our bromonium was on the top face, our bromide would add from the bottom face, and we could have the opposite arrangement of these bromines, where the bromine on the left is on the top, the bromine on the right is on the bottom, but they will always be trans. They will always be anti to one another. They will never be syn. So here we are, back to 7 reactions. Let's summarize it looking where we're starting. I'm starting with an asymmetrical alkene, and I'm doing that so that in our reaction map, I can illustrate Markovnikov versus anti-Markovnikov. So looking at our starting material, the Markovnikov position is the more substituted carbon right there. Our anti-Markovnikov position is the less substituted carbon. So here's HBr. Remember, that goes Markovnikov. The bromine goes on the more substituted carbon. The H goes onto the carbon with the most H's. So that's our product for Markovnikov addition of Br. Then we did anti-Markovnikov addition of HBr. That follows the radical mechanism that gets initiated by H2O2 or some other peroxide. That forces bromine to go on first, and therefore it goes on to the anti-Markovnikov position, leaving the Markovnikov position for the H. So that's anti-Markovnikov addition. Then we did Markovnikov addition of alcohol. So again, our OH going on to the more substituted position and the H going on to the less substituted position. We can do that two ways. We can do that with acidified water, H3O plus and water, or we can do it with oxymercuration, demercuration. First, we add our mercury acetate in water, then we add NaBH4. Two ways to give Markovnikov addition of an alcohol. We also looked at Markovnikov addition of an ether doing alkoxymercuration, demercuration. Instead of oxymercuration, it's alkoxy. And again, we use an alcohol in our reagent instead of water. And that gives us OR instead of OH, but it's also Markovnikov. It's the same mechanism as oxymercuration. Then we did anti-Markovnikov addition of HOH. That's a different reaction, again, different location of the OH. It goes anti-Markovnikov, but it also goes syn. So I'm including stereochemistry here because it matters. The OH went up in this case, which means the H on the other carbon must also go up. In this case, that puts the methyl group down. So we get enantiomers in that case, like I showed you here. We get enantiomers where the H and OH go syn. They can add to one face or the other face, syn. And then lastly, adding Br2 across a double bond gives us our bromines anti, so we can also get enantiomers in that case. So 7 reactions: Markovnikov HBr, anti-Markovnikov HBr, Markovnikov OH, anti-Markovnikov OH, and then anti-bromines. I threw in the alkoxymercuration as well. Okay, so that's lecture 11, Stramanis chapter 8. That's also Wade chapter 8. Try making flashcards, try making reaction maps, try doing lots and lots of practice problems. Learn the big picture and learn the mechanisms. The mechanisms will explain the big picture. So you have to know both sides of that coin. Good luck.